These are a reference for voltage regulated power supply. So if we were to look at the schematic of like a LM7805, somewhere in there is going to be a thing. We use these to clip circuits. We use them to make sure too high of a voltage don't get into something. We use them to trigger fault circuits on power supplies. So if the voltage on the output of the power supply tries to go up so high and cut off the power supply, so these are used for safety. These are also safety to equipment. These are also used for low voltage, especially low power supply. Very simple circuit. Set it up. So what I did is I went in there and found a Zener, and then questions. So y'all all okay? Zeners? That's surprising. Of course, we'll find out on the test, right? So our transformer is sealed inside a train, but y'all need to know, and it's not labeled right. That's the biggest problem. It's labeled 6.3, 6.3 is 0, but that you'll never find a transformer label on it. So this is very. So this is a transformer, and this is the actual label on it. 110 volts, 60 hertz, red lead, secondary 12.6 VCT. So we think VCT, center tap transformer. But it don't say 6.3, and it don't say 0 on the center tap. It's whatever you make it to be, right? So I don't like the way the trainer is labeled. And then it comes up and gives us the color code. It tells us that red is your primary. And then it tells us, this is obvious. Which one would you think would be the center tap? The blue. Good job, yeah. So these are the two outsides. So if I wanted 12.6, then I would use the two outsides. If I wanted 6.3, then I would use this. Of course, if it's a full wave center tap, then I'd have to use all three. This is the transformer that's in the trainer. And this is what we call a multi-winding transformer. So we can have more than one winding in the primary. Usually multiple windings in the power primary is so you can set up for different input levels. But most of the time factories have more than one voltage. So when you get over in, if you take motor control, that's part of your class, then the type of transformer we have over there is has two primary windings. Let me get my camera that way. So the two primary windings. And what do we use transformers for? What's that? Step up voltage or step down voltage. But that's what we say. But also it's changing the current. What it don't change is the power, right? You understand that? So, I think that was on the last test. And I think nobody in the class got that right. So if you was to come here and apply for the job, you would get hired. I know I told you. Power in equals power out, guys, times efficiency. So we can't create, sorry, I don't know how to, what work in equals work out times efficiency. So we never have more work than we put into it. We never can create more work than we put into it, no matter what you do. So this transformer is it's a dual winding transformer, and basically it's on the primary, so it's set up like this. And on most transformers, by the way, especially industrial transformers, the high side they label with H, H1, H2, H3, H4. And then over on the secondary side of transformers are labeled X, X1, X2. So what we can do is on this transformer, I can bring in 240 or I can bring in 440 and I get 120 volts out, no matter which way I wire it. So if I bring in 440, we want more turns on the primary than on the secondary. So what we would do is we would connect H1 to H2. We hook them in series because the current in the primary is going to be lower because we have a lot of windings, right? So the high voltage side. And this gives us a divide by 2. So we wire divide by 2. So let's just, for purposes, let's say this is 100 windings. This is 100 windings. And this over here is 50 windings. I'm sorry. Yeah. So this would be 250. That would give me a divide by 4, right? Okay? Now, if I wanted to hook it up for low voltage on the primary, that means the primary current has to be bigger because the voltage is going down. So what we do is we come up and hook them in parallel, so each coil shares half of the current. So what I'd have to do is I'd have to come up here, and you got to do this right. I'd have to have H1, and I would connect it to H2. If I connected H1 to H4, then the transformers would be what we call bucking. It wouldn't hurt the transformers, but you'd get 0 volts because the two primaries would cancel each other out. Yeah, H1 to H2. I'm sorry. No, this is 2. H1 to H2. Yeah, it is. I'm sorry. Sorry to confuse y'all. And it looked like a 2, but you're right. You're exactly right. H3. So 2's right up above that. So H1 to H3. And then I'll take H2. And I would connect it to H4. And what you always do as a standard is your line would feed in, always feeds in on H1 and H4. So here the windings are hooked in parallel. So now my turns winding, this has got 100, this has got 100, but I got them hooked in parallel, right? You understand? So it'll be 100 on the primary. Now we can get twice. Now the current in the primary doubles, but it's split between two coils, and I would still get 120 volts out. Now when they draw this thing, they'll draw the primary like this, and I'm going to do it vertical because it's easier to draw this way. When they draw this thing, and when they wind it, this is the way they bring the leads out. So they come up here and do this, and this might be H1. Then this crosses over. This would be H2. Then this crosses over, and this is the way it's wired. H3. This would be H3, and this would be H4. This is the way it would actually. So if you looked at the terminal, the actually screws or whatever that hooked it up, it would go H1, it would go H3, and then it would go H2, and it would go H4. Now why do they do that? So what you do when you buy the transformer, it'll probably come with these two little metal straps on it. And what you do is depends on how you want to wire it. So if I wanted to wire low voltage, then I would put that little metal thing from here and here. And if I wanted to wire it for high voltage, then I would put my little metal jumper, I would just come over and put my little metal jumper right here. So when they cross it like that, you have no crossing wires. So now it'll come with two little jumpers on it, two little metal things that you can slide right up under the screws. And you just go between these two for low voltage and between the center for high voltage. A lot of people want to know why they cross them like that. Why is the screws like that? Why are the screws labeled H1, H3, H2, H4? They say, well, why you need H1, H2, H3, H4? because of what it does, it gives us the ability to set it up for high voltage or low voltage with these little metal jumpers that comes with the thing. So it's pretty neat. So this is what's on the trainers over in motor control. So if you take motor controls, what thing you're going to have to do is wire the transformer. In fact, we have a lab where you wire the transformer. Now, the transformer for the trainer, it has multiple, I don't know how many it's got. So it's got one, two, we'll look at it. But it's got all, so this is the trainer's transformer. So this is the trainer's transformer. Black and white, this is the primary, and all these over here are the secondary. This is not the same transformer. That is what we call a dual, we call it a dual primary transformer, which basically, if it's got two primaries, it's in there so you can wire it for different voltages. This is not a H1, H2. We'll have to look at that because this guy's got a ton of them. Okay. So we'll see how they got it labeled when we look at the schematic. So this is a multi-winding secondary. Now, why would we need multi-winding secondary? Different output voltages. Yeah, so now we have different output voltages. So if we come over here and we actually look at the schematic, the power supply schematic for the trainer, which we've already looked at before. By the way, this is in that reference material section of Blackboard. Yeah, this is what we're going. This is the actual power supply. So we looked at these yesterday. Or I'm sorry, not yesterday, last class. We just took a glance at them. And then this would be in the handout section. And then supposed to be in here. Oh, I think I had a PowerPoint set up for it. So these come in backwards. Power supplies, filters, trainer power supply. So these are actually schematics that come with a trainer, but they're actually sideways, so that's why, and it shows you, regulators will actually open up the trainer and let you actually look down and find this stuff. It says I don't have it activated, but I do. So this is the actual power supply for the trainer. Power supplies. So here's my primary. Here's the little neon bulb that comes on inside the power switch when you turn it on. Here's the actual fuse. I'm sorry. Here's the power switch. Here's the fuse. And these are your windings. So it's got one center tap transformer. And they're not giving us H1, H2. They're giving us the colors. So yellow, gray, and yellow, that would be the center tap transformer. And then this guy right here is red and red. So it don't make any difference which one is different. It's a transformer, right? And then this one down here is another center tap. So this is the one we have right here. It's a 12.6 volt center tap transformer. This is not 0 volts. It's only 0 volts if you wire it to be 0 volts. And that's what I don't like about the trainer. And why they did that, I have no idea. I doubt it was somebody that wouldn't get a job here, right? And then we come over here, so this goes over to a full wave bridge. Here's our filter. They're using a 470 microvolt 16 working volts. So this is probably 5-volt supply. So it probably won't be under there. It'd probably be under trainer power supplies inside reference material or trainer manual. So it's the trainer is a PAD 234A. Yeah, and you can buy this guy, but you can buy it as a kit, and it's like $100 and something bucks as a kit, but you have to put it all together. And if you hadn't had soldering, you'd be in trouble. I think the actual cost is around $230, so it's not, consider what it does, it's not a bad price. I'll look and see. It should be up there. Like I said, I didn't set up this site, so some of the stuff might not be up there, so that's a good point. If you don't find it, you need to what? Yeah, now this guy right here, we'll have to look at this guy right here because we see it as a full wave bridge, but it's actually a full wave center tap. Now the telltale is this center tap is connected to common. This one, the common is not on this side. The common is on the rectifier side. So what this is this right here has two. This one here. If you look at this one has two anodes pointing, so this is a positive supply. This on this side has two cathodes pointing, so this is a negative supply. So this is kind of misleading. It is a full wave bridge. It is a bridge rectifier, but they're wiring it to do half-wave center tap. And what you should see is on a full wave bridge, the transformer is not connected to the common. Over here on the full wave bridge, on the center tap's connected to common. And the only one where the center tap is connected to common, unless we're only using one half of the transformer, is when it's a full wave center tap. And these are 7800 series regulators. So and they're really neat because if it's got 78 and 12 means it's a plus 12 volt regulator. 79 means it's a negative regulator, and then they give you the voltage phase. So 7912 is a minus 12. A 7812 is a plus 12 volt regulator, and this over here is a 7805. So what do we think that would be? 7805. Y'all ain't caught on to this yet. So a 7812 is a 12 volt regulator. 79 means it's a minus regulator. 7912 is a minus 12 volt regulator. This is a 7805. So what would this be? Plus 5 volts. 78. So 78. So these are regular regulators. These are all over the place, guys. 78 identifies it as some type of positive regulator. 79 specifies it is a negative regulator. 7812 would be a plus 12 volt regulator. 7912 would be a minus 12 volt regulator. And a 7805 would be a 5 volt regulator. And these are used all over the place. And we'll show y'all where these are actually mounted on the trainers. They're heat sinks, and we'll talk about that. These are your variable regulators. So these are the ones that allow you to adjust the output. So we'll come back and look at these. So what I'm doing, so we'll pass this around and y'all can and I'll put a wipe on it so y'all can wipe it off and I'll pass it around. So this is like 6 bucks center tap. And then this is the trainer regulator. This is the trainer problem. And like I said, these are not labeled H's. Those are adjustable transformers. But it would be cheaper than buying 3 transformers. So it would be cheaper for me to replace if it was different transformers. But it's cheaper for the company that builds them to use that. So yeah, what the company's doing, they're not thinking about you. They're thinking about, how much does it cost to build it. And this is such a unusual transformer that they might even have this wound specifically for this train. But it still would be cheaper than trying to buy 3 individual transformers. Does that make sense? So good question. So what I wanted to do is I wanted to build a power supply where you could actually see everything within the power supply. So I started off and I've got a 1N, I've got a 1N 47, undoubtedly I closed my, I've got a 1N, it's 4744A Zener. So I just went in there and picked out one. So what is a 1N 4744 Zener? And it's an A. We need to figure out what that A means. So there's a difference between a 1N 4744 and a 1N 4744A. So what is a 1N 4744 Zener? About now, I think I would get up and I would come over and get one of these data books over here and look this up. Helps keep social distance, right? Of course, the data book is on Blackboard too. But you said the trainer schematic wasn't up there, Mario? It is. It's just in the wrong. I can understand it, but it's up there, right? You find it? Oh, there's okay. So 1N 4744A. So let's figure out what's the difference between the A so this is on test code. So solid state, data sheet, 4700. This should be the same one that you have in your data book. The one that's in the PowerPoint slide is not exactly the same. I need to change that over because it makes it a lot easier if they are the same. So these are all 1 watt Zeners. Let's zoom in on it. So here's a 1N 4744, so it's a 15 volt Zener. And then ICK is 250 micrograms. And then I'm looking at this little note right here, tolerance and type number designation. The JEDEC, this is the Joint Electronic Device Engineering Council, by the way. These are guys that creates a database of part numbers that are open to anybody. So it means if I come up here and I want to create a 1 watt Zener, a 1 watt diode, and it meets this specification, then I can give it the number 1N 4744. So these are open specs. So I've got a part, and a lot of these parts are like this, especially in the first part of the technology where everything was open. So what does it say down here? Note 1, it says tolerances. The JEDEC type numbers listed have a standard tolerance on the normal Zener voltage of plus and minus 10%. A standard tolerance of 5% on an individual unit is also available and is indicated by a suffix of A to the standard type number. So that means ours is a 1 in 47, 1 in 47, 44A, so this is plus or minus 5%, right? So understand that? So here's a Zener. It's a 15 volt Zener. It's got a Zener test current. That's opposition. It's got a Zener. It's got a knee current of 250 microns, and that's about all we need to figure out how to design this. So my circuit, I come up here and I got a center tap transformer, but I'm using the whole transformer. I'm not going to draw the center tap. And then I come over here and I've got a full wave bridge. And I'm creating a positive power supply. So I had to come up with my series resistor, RS. And then right here, right here I got my filter capacitor. And this is 100 microfarad, 50 volt. And then of course my Zener's right here. And then my load's in parallel with the Zener. This is 1 in 47, 44, which is 15 volts. And as my load, I'm using I don't have a load in there. So I'm going to use I'm going to use the 130. So this is 1K. And your diodes are supposed to be colored in, but most people don't. And that's the way you don't confuse it. I'm going to come back and redraw this the way we would see the schematic. We would not see this wire down here on the schematic. What they would do is they would have either the symbol for ground or the symbol for common. Now the only way that would be ground, if I came over here on this side and we ground one side, and then I come over here and I reestablish the ground on the other side of the fence. That's the only way that would be grounded like that. If I don't do this, even if I ground that side and I come over here and do this, then this would be a common. It would not be a ground. Now, whether you call it ground or whether you call it ground or whether you call it common, that's okay. It's just that you need to know the difference between ground and common, which this guy, whoever engineered this trainer, really got confused. So how can you tell if it's grounded, the trainer? So it's got that black thing over there, and they call it G and D. How can you tell if it's grounded? Well, this has got a 3-prong plug on it. Well, what I would do is I would take my own meter and I'd hook it on that ground, and then I would go to what you said, that little 3-prong plug. I would hook it up to there. If it measures 0 ohms, then it's grounded. If it don't measure 0 ohms, then it's not grounded. So I can come over here on this trainer and I can get my voltmeter. Make sure I maybe I'll and I'm gonna come over here, and I'm gonna go over here, which Cameron said is I'm gonna come over here and hook this up. So we know this guy. Let me tab. Let me get my. So here's my camera. I'm gonna go full screen, and then I'm gonna swing it down so we can try to swing it. So what I'm gonna do is I'm gonna come over here. I'm gonna put my turn my thing on. I'm gonna put it on. So let's put it on continuity so that way it'll beat that. By the way, this thing shows that when the meter's open. I'm gonna come over here on this center thing. I'm gonna put that on there, and then I'm gonna come over here and I'm gonna take my other lead, which is my black lead, and I'm gonna put it on this thing they call ground. Now, if I touch the metal case of the trainer, so the metal case of the trainer is grounded. You don't see what I'm touching? So this is grounded. But when I come over here and go to this guy right here, which they're calling ground, you didn't hear it be. So this is not ground. And this is a big misconception. So people say, well, the trainer's grounded. But notice, what am I measuring to? The ground on the power plate. So that concerns me too, about them calling it ground. Now on these other big trainers, the big power supplies that I came over here and hooked up to break that diode over, they don't label it. They don't label it ground. They label it common, which means they're telling you that that is not grounded. And what they got on the back, the chassis grounded. They got a green plug. They got a green jumper back there that's grounded, and I could run a jumper over to my common, and then it would be grounded. So you're right. So just because it's got that center thing on there does not mean the electrician hooked up the ground. So that's something that get people in trouble. So okay. So where's my power supply? Here we go. What happened to my drawing? Okay, so I'm going to redraw it. So here, if I don't run the common through, then technically what I should have done is, this is the symbol for a common. And that's why, this is why you cover in the diode, so you don't get it confused with the symbol for a common. And then I come over here, and then I'm going to drop down. And we can't use common because we're using a bridge, by the way, sorry. So the transformer can't be common if we're using a bridge, right? And then I came over here and drew my diode. And it's easier for me to draw a full-wave bridge, drawing them like this, and trying to draw them in a diamond shape. Now over here what we've done is we've established this right here is the common. So that's why I knew when I looked at the schematic for the trainer that that top one was not a bridge rectifier because they had the center tap connected to common. Then we come over here, and right here I put my filter right out of the transformer. Sorry, that's wrong. Yeah, right out of the, not out of the transformer, it's right out of the regulator. Not the regulator, the bridge. And then we got our series dropping resistor. Then we have our Zener. And then we got our load. I think I said I'm using 1K resistor. And this is 100 microfarad. So you see the trainer is going to be filtering a lot better, but it's doing a lot higher currents. Of how fast the capacitor charges and discharges It charges extremely fast because the only resistance in the charging path is the resistance of the diode and the resistance of the transformer, which is very, very low. Okay, so we're going to design this. So first of all, let's calculate my voltage right here, or approximate voltage, but it's going to be close. So what do y'all think the voltage that should measure right there? And this is 12.6 volts. I'm all the way across the transformer. I'm not using the center tab. So what should be the voltage right there? Yeah, these are all silicone. These are all silicone. Well, I don't have it in front. That's a good point. This is a 1N47. I erased the wrong thing. This is a 1N4744, which is 15 volt Zener. This right here is 100 microfarad at 50 volts. Sounds like it's kind of wrong because I'm using a 15 volt Zener and you're only giving me 11 volts to regular. Now, what you're forgetting about is that capacitor right there. So you're solving, you might be solving for this. You might be solving for this, but that capacitor gives us this. If this is 0, our capacitor is giving us this. So what we usually use, guys, is so close. If we choose the right capacitor, it's so close to V peak, we just use the V peak. Because the capacitor charges up to V peak. But the problem is, if we go through all these unregulated, unfiltered power supplies, and that's the formula you want to use. So here, I'm going to say this output right here is going to be equal, pretty close, approximately V peak out. Because that's what the capacitor charges up to. What do you mean by trace it?
So, the way that I got my calculation wrong, that I took the wire out and I went up, straight up, and I subtracted 12.6.
Well, you don't subtract 12.6 minus 0.7. You subtract the 0.7 from VP. So that will give you a lot lower than what we're supposed to have. So it's V peak out, V peak out equals V peak secondary minus 1.4 volts. Not, you don't subtract it from the 12.6, you subtract it from VP. So I'm going to take 12.6, so V peak secondary would be equal to 12.6 divided by 0.707. And that would give me V peak secondary. So what we got? 17.8 volts. 17.8 volts. Then I would subtract 1.4 from there. Does that give us that? $16.4. Yeah. Then I take 16.4. Then I would divide it by pi. No, I'm sorry. That's where we'd stop at. This is V peak out. So that means we got about 16.4 volts to work with right there, which is close to the regulator, but so if I come over here and I look at my power supply between my camera background. Then what I'm gonna do is so here's, get it in closer. So here's my center tap transformer. Of course, here's Q in line with the primary. I'm not using black, so I have it taped over. That's the center tap on this transformer. This comes into my four-way bridge. I'm using an integrated four-way. So this is AC, this is line, this is AC. You're going to run into these a lot because it's cheaper to buy one of these for the company putting it together than it is to buy $4. Now it would be more expensive for me to repair, right? You understand that? Because I'd have to buy the bridge, but it's cheaper for them to. If I had one diode go out, then I could replace one diode, but I can't do that. So you're going to see a lot of these guys. We got one that's rated like 25 amps. Here's my series dropping resistor. Here's my capacitor. I have my capacitor in parallel with DC plus and DC minus, and I make sure I honor my polarity, right? Here's my series dropping resistor. Here's my diode, and here's my load. And I just saw. What I'm gonna do is I'm gonna measure with my voltmeter. I'm gonna measure what I get out of my full-way bridge. So that would be, somebody, one of my things that I made for my, the boom I made for my phone. So I'm gonna measure the output. So I'm gonna go here, plus, minus, it measures 17.75. Pretty close. So on these guys, if you choose the right capacitor, then your output voltage is going to be really close to DC out.
And that's the, what you have there is the schematic, right?
Yep.
And I think it's because that's
Oh yeah. So VP out, I'm using a 1K resistor. That means my load current is around 17 milliamps. But we'll say, right, 1K, we're getting about, well, I'm sorry, we're getting 16. What volts are we getting right there? It's about 17 volts. So over here, that'll be about 17 milliamps. So let's vary it. Let's vary my load from up to 20 milliamps down to 16. What size resistor do I need for RS? Let's let the input vary 5%. So that's going to be 17 volts. Volts is for what we calculate.
my question was, I think what you're saying, how do you get that 17 volts?
I don't know. That's a good question. It's recorded.
Okay.
But what we should have done, right off the bat, we should have got this. So we should have solved for VRS minimum and VRS maximum. But when you get into a hurry, you get into problems, right? But it showed up in the design. So what happened is when I came over here and I measured the output, I was expecting 15 volts. But when I measured it, it was 10 volts. But it's a 15 volt Zener. So that had to mean that RS is dropping too many volts, which means it's too big. So what happened is that in my hurrying, I left all the major steps. So we said we're going to allow the input to change, what did we say, 5%? So we measured what? What was our peak voltage, 16 or 17 volts? So my maximum voltage, peak voltage, would be 17 times 1.05. And then my minimum would be 17.95. So, what does that give me? 17 times 17.85, and then my minimum voltage would be what? Now, that means my maximum voltage that resistor would have to drop would be equal to 17.85 minus 15. And VRS minimum would be equal to 16.15 minus 15. So what we did is we calculated that resistor to drop that voltage right there, but that resistor doesn't fit. Okay, sorry. Thank you. So what would 17.85 minus 15 be? What's that? And then 16.15 minus 15. I'm listening. Okay. So we want that resistor to drop the minimum voltage over the maximum current. So our rush to get this through, we dropped out a vital step. So this is going to be 1.15, not 16.5, over, and then my current was, I forgot, what current did we use? Okay, 20 milli plus 0.02, 250 micro. So I had the right resistor in there to start off with. And I should have noticed that. So, what did this come up with? So y'all see what we did wrong? What did we do wrong? We used this instead of this. So we used the minimum voltage, but that was the minimum voltage on the left-hand side of the resistor and not on the right-hand side. So we didn't use the voltage the resistor dropped. So when we say R is equal to V over I, this is not the voltage applied to the circuit. That is the voltage that the resistor drops. And 15 volts. That's my Zener. I'm putting 16.15 volts right there. Kirchhoff's law, if I put 16.15 volts right there and calculate that resistor, then I'm forgetting about this guy over here that needs what? That needs 15. So what we didn't do is we didn't calculate the minimum voltage that resistor is going to drop. So to calculate the size of the resistor, it's not how much voltage is applied to the circuit, it's how much voltage that resistor drops. So if I came over here and I said this drops this drops 10, this drops 6, this drops 6. This drops 6. And my, okay, thank you, Jesus. Thought my marker stopped working for a little while. So this would be like me coming over here and I say, okay, this guy's dropping 15 votes. And then I'm putting 16 volts over here. And then using 16, and it's at 20 milliamps. And then I use 16 volts to calculate the size of that resistor right there. That's not true. This guy right here would be dropping 1 volt because of Kirchhoff's voltage law, right? So when we solved for that resistor first, we said VRS minimum was 16.15 volts, right? And we used that to calculate the size of the resistor. But that's not the problem. The problem over here is this guy right here, this Zener, is doing 15 volts. So if I want to calculate that size of that resistor, I'm not going to use 16 volts. I'm going to do what? According to Kirchhoff's law, I would say what? 16.15 minus 15. And that would give us, so we came up and got, what would be the minimum? I erased it, guys. 1.15 divided by 20 milli plus 250 micro. 66.8 ohms. This is the calculated though. So what you'll do is you'll start off with calculated, and then you'll come back and figure out which one you're going to choose. What is that? What? I don't have a 51 ohm resistor. So let me see what facts. So I come over here, I have unregulated filtered over here, so I have a filter. You might have a pre-filter on these too, but it's usually real small. It might be like, 1 microfarad. And then we come over here and it needs 3 terminals. It needs an unregulated in, and then it needs a regulated out, and then it needs common. So that's a 3-terminal regulator. That's what you're holding in your hand. Well, the problem is, if I've got 20 volts on that side, and then I've got 15 volts on this side, and my load is pulling, it's a 1 amp regulator, and it's pulling 1 amp. That means this guy right here, between this input and that in, it's dropping 5 volts, and it's dropping at 1 amp, so that thing is trying to dissipate 5 watts worth of power. That makes sense? So it's just like a resistor, in and out. So what we have in, what we have out, and what flows through it. Well, the problem is that when they make this thing, they don't make it to be able to it's the device itself to be able to dissipate 5 watts. So what they do is they have this nice metal tab that comes up, and it's got a screw hole in it. Well, what we do is we take that and we attach it. So basically, thermal resistance is we calculate thermal opposition almost exactly the way we calculate Ohm's law. So all these devices have what we call different thermal resistances. And if it's real low, then it can transfer that heat. If it's not real low, then the heat stays into the device. So what we do in metals, and it just about follows the good conductor. So the best conductor of heat would be silver. Well, we're not going to do that. The second best would be copper. So we see a bunch of copper heat. These are the very, very expensive ones. Of course, the most popular or the most widely used heat sinks are aluminum. They just make them a little bigger. So what we'll do is we'll just come up here and take this tab and we'll mount it on a piece of metal. And then all of a sudden, even though this thing is very, very small, now the heat sink is all the metal that it's mounted on. Now a lot of times this tab is electrically, it's got power on it. So normally what we have to do is we have to put some type of insulator in between there. So we'll put a little thermal insulator. And it's going to have something that has very low thermal resistance. And then we'll have a screw up here on the tab. And then we'll isolate it through the screw hole. And I'll show you all that on the train. And these are called heat sinks. So we're running into heat sinks all the time. I'll show y'all. So this is the actual trainer. Here's the multi-secondary winded transformer right here. And then these two wires just go directly to that. This one right here goes to the fuse. Here's the fuse. And then this is the way they connected the output of the transformer, the secondary, to the trainer. They have a connector. And of course, blue, orange, blue. This is one of our center tap transformers. Yellow, or second, not transformers, center tap winding. Yellow, gray, yellow. This is the other one, and then the two reds. This is the bridge rectifier right here. Oh. So it's a little integrated circuit, and I say you're going to run into these a lot more than you are individual diodes. So here's the bridge rectifier. Here's the filter. Rectifier. And here's one of the regulators right here. And it's mounted on a heat sink. That's it. Mounted on a heat sink. So that's what this guy is. It's the metal towel sticking out of the heat sink. That is the 7912. So this is the negative regulator. Here's the other regulator. This is a 7908. I'm sorry, not 7812. This is the 5 volt. We have to figure out where the capacitor's at. But here's the 5 volt regulator on the back. This is the thermal insulator right here. This is the electrical insulator, but it's also a thermal insulator, so it's got real low thermal resistance. It's got a real high electrical. This is the mount. I'm going to show you. So this is the actual mount. This is on the back. There's a little plastic insert which we can't see that goes through here, so the screws don't touch the metal. So here's the screw mount right here. You see this big old metal tab runs through there. And then this black wire connects to the metal tab, so that's connecting it to the shell right there. And then here's the other two wires. This one goes to one of the pins, and then this right here goes to one of the pins. So one of the pins. We call these things that we mount these things to the actual carries current. We call those pins. And you really see that on the integrated circuit because that's sticking. So those three terminal regulators that we passed out, those three things coming out the bottom, we call them pins. So that's the way it makes the connection. Here's the variable regulator right here. So they're using the whole metal shell of the trainer as heat sink. It's got that thermal insulator there because the tab itself is electrically hot, so it's got a thermal insulator, that little gray thing under there, which is a good thermal conductor, but it's a poor electrical. So this is the LM37, which is the negative variable regulator, and this is an LM17, I think, which is the positive. So that's the power for the train. That's the power for the power supply. Now, this circuit card is not really hard. It's pretty hard to get out, but it's manageable. So this guy is very recursive, and they're not hard to troubleshoot. Normally, when we troubleshoot, we start on the output and work toward the input. So we don't start to see if the input's okay. We start at the output. So if I came over here, and these are pretty deep because they got LEDs on them. So normally, if you have problems with one of the power supplies, the LED is not working, it's not on at all, or it's a lot dimmer than what it's supposed to be. So usually that's a good indicator that we have. And what we would do I have my trainer schematic still up? I bet I don't. Should do. So this is the way your three terminal regulators work. There's still three terminal variable regulators, but what we see is we come over here and we have a pot wired as a rheostat, and then now that third lead or the middle lead or whatever it is not connected to common anymore. It's connected to an input called adjust. And then this is the output. So here's our output right here. And then this feeds back to this guy. And the ultimate goal is to maintain, I think it's like 2 volts, but we'd look it up, between these two pins. So if this output dropped down, then what would happen is this would automatically turn it on more to do what? To maintain the same output. If it tried to go up, it would automatically adjust back. But these are actually given to you, and that 2 volts would not be there, it would be right here. So if I start turning this down, this voltage would try to go down, which would cause the thing to automatically raise it back up, get 2 volts. And so this is the variable regulators. This is the LM37. This is the minus 12 volts. And then this is the 17. This is the. But what you got to look, and we want to see this as a bridge rectifier. Well, technically the device is a bridge rectifier, but it's wired to do full wave center tap. And the telltale is this guy right here. So they've got they're using the center tap on that transformer. Down here, the common is set on the other side of the diode. On a full wave center tap, the common is set on the transformer of the diode. So if we follow this through here, then of course this would be positive. So we go here, go through my regulator, go through my load, come back up to the center tap, and go to this side of the transformer. And over here we have cathodes pointing toward this side. So this would be your negative. So I'd come through here, and I should do that as a different color, but I'll do it from here on. This side or this way, and this would be this way or that way. So that gives somebody a little problem because you learn these and you want to think this is a full wave center tap, but it's not. It's a full wave. I mean, you don't think it is a full wave bridge, but it's actually a full wave center tap that's using a bridge rectifier. And then this right here would give us our minus. So like I said, these LEDs, they run off about, they usually run off about 20 milliamps. And this resistor sets that, it drops the difference, and we'll look at these later on. notice the cathode is pointing toward the negative. Over here, the anode is pointing toward the positive. So to make these things light up, you got a forward bias. So if this thing's out, if this thing right here is off, then we know that either the LED's bad or the regulator's bad. But what we do is we just come over here, we take our meter, measure there, and it should measure minus 12. And then we would go over here and see if it had minus whatever. We know it's going to be, we know over here, if this is minus 12, we know over there it's got to measure more than 12, right? But you can't get more out than you put in. So we go from here, go from there. Then we go over here and check the AC. If I had AC, I didn't have anything here, then odds are we got a problem with our bridge, which we've had before. So these linear power supplies are real easy to find out the problem. In fact, I wish I could find that trainer. But we had one of the bridges that went out on us, and we didn't have one that would fit in that slot. So I literally took 4 diodes and just hooked them. In fact, they ended up looking like that. And I made a bridge rectifier out of 4 diodes. Plugged it into the hole, and it works great. So I don't know where it's at, but because we didn't have that little diode. Probably we could rearrange. We could probably I didn't put my things up. We probably, if we would have had these at the time. Yeah, well, it's too late. That's the problem with the wheelchair. So I have it all the time. Now we have to look up this part on this one because it doesn't tell me. Well, that's probably why. So we probably could have made one of these work. But the problem is that we don't have the specs on them. But we probably could have, but you can actually see the leads. So these, and I need to show you how to check these with an ohm meter. If it's going to focus in. We did a real good job with it. But this is AC, this is AC, this is DC minus, and this is DC plus. We probably, if we'd have had these, we probably could have made it work, even though I don't know what it's rated at. But we didn't have these at the time. Somebody donated these. So, let's go back and see how we check these, and then we'll go to lab. And my mouse stopped working. Oh, I unplugged it. So we know how to check. By the way, Zener's, if you check Zener's with your ohm meter and you put it on the diode scale, it will check just like a regular diode. So you can't tell that. You can tell if it's good or bad, but you can't tell if it's a Zener or whether it's a rectifier diode. So I've got this thing right here. So how in the world would I check this to see if I had a bad diode inside this right here? So I'm going to draw it the way I like to draw it. It's easier to draw. So these are the wires coming in. This would be labeled AC. This right here is labeled AC. This up here would be labeled plus, and this would be labeled minus. So how do you get a minus of power supply? Well, you just use this as your hot lead and use that as your comp. So you don't have to swap diodes or anything. It just depends on how you hook it up. How would I check this to see if I had a bad diode? Because I don't see the diodes. This is what I see. I see 4 leads coming. So this right here is what I see. I see 4 leads coming out of this thing. So I'm just going to draw a square around it. This is what I see. So how am I gonna check the diodes inside this one? To see if they're good or bad, see if it's good or bad. Well, the problem we have, and that's a good point, but the problem we have is usually my meter won't put out 1.4 volts. So normally what we do is we'll come over here. This is the way we check it. So I come over here and like I'll put my, I come over here on my AC and I put my black lead right there. And then I would come over here and I would put my red lead on this one. See that? And then what would I do? So my black lead is right here. I'd put my red lead on this one, and I'd put then I would red lead on this one. So here's my black. I'd come over here and touch this right here with my red lead. And which diode would I be checking? So let's call it, yeah, bottom. Let's call this 1, 2, 3, 4. So here I'd be checking diode number what? 3. Then I would leave my black lead right there, and I would move my red lead up to here. Which diode would I be checking? Let's do this different. This is harder than it needs to be. Let's do it this way. So put black lead on the positive. Okay. Then I put my red lead right here. Which diode would I be checking? One, two, three, or 4. You got 1. Then I take my red lead and I move it down here. Leave this alone. Then I take my red lead and move it down here. I can't get to all my colors yet. So then I take my red lead and move it right there. Which diode will I be checking? Checking diode 2. So we did 1 and 2, right? Can you see how we're coming? You okay? Then what would I do? I need to check these 2 diodes down here. So right now we checked what? We checked this one. Put my red down here. And then I'd come up here and do what? Put my black right there. This will check what? 3. Let's go back and look at the other one because I think I did. I think we got that one. What did we start off with? We started off with our black lead right here, right? Then I came over and put my red lead right there. So which diode would we check? So y'all was right. We would check what? 1, and then what would I do? I would leave this up here and do what? Move it right down there, and that would give me 1 and 2. And then we'd come over here and do what? So we need to check the bottom 2 now. So so what we would do though is we take the black lead We take the black lead, no, we take the red lead and put it right here, right? And then we come over here, we take the black lead right there, and that would give me what diode? That'd give me 3, right? And then I would move my black lead down here, and then that would check voltage. So what we do is we come over here, and this is strange because this is labeled plus, but what did we do to check it? We put the black lead here. This is labeled minus, but what did we do to check this one? We put the red lead down there. So it's opposite of the sign. Does that make sense? To check it. And then you move your other lead between the two ACs. You can check all 4 diodes. And you got to do that because why? Because if one diode goes out, what's going to happen to your power supply if one diode goes out? If it opens. You're right. If you got one that shorts, you got a short circuit, and that's going to blow the fuse. Okay. And that's something to check. So if your fuse blows, then this would be one time you would check the diode, right? So what would happen if this diode right here opened? Well, it all depends on how big capacitors you have, and there's a lot of situations. So what happens is what we got is we went from this that we're filtering. So this is what we're getting out of. We went from this, and then when we filter it, we're getting this, right? So what happens when we come over here and lose one of our diodes, we go to this. So what that means is my ripple voltage is going to be twice what it was, because now instead of the capacitor running the load for 8.3 milliseconds, it's running the load for 16.6 milliseconds. So my ripple voltage will come up in what, double. Now, if you got big enough capacitors, it might take care of that. But if you don't, and if you put enough load on it, then if the 15-volt regulator, all of a sudden what's going to happen is your regulated voltage is going to, your unregulated voltage will get into your regulated voltage, and then your output voltage might drop down to 14 volts. So the output voltage will be low. So if the output voltage is lower than what you expect, then there's a good chance you got a loss. Now, if it's an unregulated power supply, your output voltage will drop to 1/2 of what you think. If it's a regulated filtered power supply, it's not going to drop by 1/2. It's going to depend on the size of the capacitors, how long they can run the load. But your output voltage may go down. So that's the way you check them. So you put your black on the plus, and then move your red between your AC. Then you move your red to the minus, and then move your other lead between your two ACs. That's the way you check this thing. And if it's bad, you don't replace a diode. You replace the whole integrated circuit, right? So that's the problem with this. So it's cheaper for them to build the trainer, but it's more expensive for us to repair it, because we have to buy that whole IC instead of just replacing one diode. But y'all, Cameron, you was right. If you get one of these things, one of your diodes short, then we'd come in here and we would replace that with a straight piece of wire. So what happens when this thing here comes over here, and this guy's forward bias, you have a short circuit, and it would hopefully blow your fuse. But there's a lot of things that could blow your fuse. You could have a shorted capacitor, you could have a shorted diode, you could have a shorted load, you could have, your load could actually be short. But that's just disconnect these, right? Those are terminals right there. Alright guys, what time is it? Well, let me run off the 5.1 volts? 5.1 volts is our design, right? On the sheet under design parameters. Then what we're going to do is we're going to hook this up to our variable DC power supply on the trainer. Yeah, so we can vary it between the design parameters. And that's what you would probably do. It's just like when you design an amplifier, you bring a signal into it that you know what to expect. You don't depend on audio. Audio is all over. So normally you use these function generators, and then you put the frequency in there to make sure it responds to the frequency range that we have. So we're going to use the plus 15 volt variable power supply. Then y'all are choosing the resistor. And then we're going to put a Zener. And then I need to do a device. I need to use a load where I can vary. I need to use a load that I can vary current with. What variable device can we use that gives us the ability to vary a current? So what device do we, go ahead. Sort of. We're going to use a pot, but we're going to wire it like that other device. So a pot by itself, we use it to vary a voltage. But if I come over here and take that pot, and I take my wiper, and then I connect it to one end, then it acts like a rheostat. So a rheostat is a current controller. A pot is we do for voltage. But like I said, you're not going to hardly find any rheostats anymore. Because I got one device that I can wire to do the function of a rheostat. And we'll vary that, but we're not going to hook that up like that because that would be dangerous. We're going to come up here, we're going to put a fixed resistor in series with it. So I don't create a short circuit and burn up this resistor. So the actual circuit would be like this. We'll put a fixed resistor right here. I think I give you the size. It's like 100 ohms or something like that. And we have to choose one that would give us the ability to so somewhere on your lab it says, okay, what Zener are you going to choose? And what do we come up with? Yeah, 3.3A. Not a 3.3, a 3.3A. A 3.3A would have 10%, but the specification says plus or minus 5%, right? Yeah, that's in the first note down under the data sheet. Oh, that's my pen. So, what we're trying to do is our input voltage, I'm going to vary it between what? So this is 5.1 volts. That's my Zener. We're choosing a 1N 4733A. Zeners, it's hard. Normally on schematics, we designate diodes with a D. But most of the time on Zeners, they'll designate it with a Z. So this would be like Z1. This right here might be R10. Even though it is RS, they're not going to call it RS on the diagram. I don't know if I can see the train. So their R's are numbered R's. And then, of course, this will be my variable power supply on the trainer right here. And this is going to vary how much according to our design? We're going to vary this over to how much? What's the maximum we're going to vary? Yeah, so VRS maximum would be equal to 7 minus 5.1. And VRS minimum would be equal to 6 minus 5.1. So this would give us 1.9, right? And this right here would give us 0.9. 900 millivolts. We okay? What's the matter, Jess? We're calculating the, yeah. So that's the diagram that we got, right?
Okay.
I think it tells you to draw the diagram of the circuit on there somewhere. I don't have a copy of that. You need something? Oh, you're coming. I can't remember what K pot, what size pot. I'll see if I got a 1K pot. It says 10K, but we're trying to get what current? It would be easier. 10K is fine. It'd just be easier with a 1K. I don't know. I need to calculate the current. So how are we going to measure current? How am I going to measure? What's the current parameters? No, what's the parameters? What's the design? No, what's the parameters on the data sheet? I mean, on the lab. 2.5. And do I give y'all the size of this resistor right here? Y'all understand why we're going to have to put a resistor in there? Everybody understand that? Because if I take this rheostat and adjust it up to there, I have 0 ohms on my load, and I would have a short circuit. So we're putting that resistor in there basically so I can adjust this thing. If I accidentally adjust it up to 0, it's not going to burn things up. But that's got to be a certain size. Is it a 1K or is it like 100 ohm or something like that? Did it say? I don't know. It's good. So that would be. So when we measure our current, we're not going to measure our current. What we're going to do is we're going to measure the voltage drop across this resistor. Anytime you have a series resistor, you can use it to calculate your current, right? You understand that? So I've seen people break circuits to measure current, and it flows through a series resistor. And all you have to do is just measure the voltage drop across the resistor, right? I is equal to V over R. See it work? Is that okay? Everybody okay? Or y'all still working on it? I'm trouble with that. So we all use 900 milli over 7 milli, and then what's the IZK?
That's all.
1 milliamp for this side, yeah. So 0.9 divided by, oh, let's see. Good job. So the next step one down on the chart, like Mario said, was 110. So when we took 110 and multiplied it by 1.05, it came up to be greater than that. So what we did, we went down to 100 ohms. And then the maximum voltage it's supposed to drop is 1.9 squared over 100 ohms. And we come up with that would give us our power on our our resistor. So we use quarter one. Good job. Actually, we could have used quarter watt, but we don't have any quarter watt. I came up with 10.065, 36 points. That what you came up with? Yeah. So we could have used quarter watt. We could have used an eighth watt, which would be 125 milliwatts, but we don't have any of those, so we're using quarter. So that's one reason you got to use what you got, but you want to make sure it's greater than what you're getting, right? And they would have probably used the quarter watt here, even in the design. Did I tell you the reason why? You okay, Lee? Okay.
So I said that quarter, well, in the quarter, but then I'm not sure how long that 3400 watt, that RD.
That's the calculator. But we're going to use quarter watt. Well, if we had it, we could have used an eighth of a watt. Because an eighth of a watt is 125 milliwatts, and then a quarter watt is 250 milliwatts. So yeah, we could have used an eighth of a watt there, but even in the design, they probably wouldn't use an eighth of a watt, because they make thousands of quarter watts, and they don't make that many eighths of watts. So the quarter watt is actually cheaper than the eighth of a watt. Just strictly because it's mass produced. I mean, we do have some quarter watts in there somewhere. We don't have any eighth of a watt, 100 ohms. I think we got some eighth of a watt 10K. And those are little old tiny things. This is a quarter watt. Y'all familiar with this? This is what y'all use. And that's an eighth of a watt. I mean, even the actual block would be harder to make. And the little old tiny things, and then they'll actually be soldered on the board right there. And then you have to get out your magnifying glass. And then they don't put color codes anymore. They put a code like this. 103. And basically it is the color code. Just it tells you the number. So that would be a 10K resistor. So it's saying 10, add 3 zeros. So when you get into these little old tiny devices, they don't use the color code anymore because the color was run together and they put these little old tiny letters on there. And I don't know if I got. So on printed circuit board, C is the designator for capacitor and R is the designator for resistor. I'm gonna put this on a barrel thing too and pass it around. So when you get into these printed circuit boards and you extremely low wattage resistors, then they'll go to these surface mount resistors. So this right here is a resistor. It's not, but if we got a magnifying glass and looked at it, it would have a 3-digit code, like 103, which would be a 1K. They can print the letters on there, but they can't put the colors. So these are capacitors right here. So they're designated C. Resistors are designated R's, and these are what we call surface mounts. So they literally have solder pads, and they just solder them to the top of the board. Of course, you know these are capacitors. And, these are transistors, which we're going to get into next. No, these are not transistors. These are labeled U, which U is usually the designator we use for integrated circuits. So you see this big old one right here, it's designated U4. So these are just 3-terminal integrated circuits. So anything that'll fit in 3 terminals will be, but if it's called a U, it's usually an integrated circuit. If it's called a Q, it's a transistor. And why don't they use T? Because T is already designated as a transformer. So if you ever look and see a transformer, they're going to call it like T1, T2, T3. So they had to give it a single letter designated. So this guy's got a lot of capacitors on it for filtering mainly. And of course, this might not even be a resistor. So it's blue. We would have to check on this. This might be an inductor. Usually it's usually a milliamp. So you'd read it, but it uses the same color code that resistors use. So anytime you see one of these off color ones like this, and it's not, like light brown like our resistors, and these are probably either capacitors or inductors. In fact, it's an inductor. How do I know it's an inductor? Well, y'all can see it. It's L1. So L1 is the designator for the inductor. C we use to designate capacitor. R we use to designate resistor. U we usually do that for integrated circuits. This is actually a gain port. So you said before we had USB, you have to buy a choice gain port. And now everything comes. Those are pretty standard on the first order. R for what? Resistor. C for capacitor. L for inductor. U for integrated circuit. So if we pass this around, you see they use the same technique. Oh, here they're using an RN, which is, it's not registered nurse. So right here, you see this is designated, I'll get my finger on it, this is designated, I'll get it over here. This is designated RN. So what it is, it's a resistor network. So what they're doing is they use the same resistors as what we call pull-up resistors. So what they'll do is they'll have the resistors like this, and then they have one pin would connect the top together, and then the bottom would be actually connected to the circuit. And these are designated for on this guy for resistor net. And this is called a SIP, by the way. Bring it back up. So this is this package. We call this a SIP package. It stands for single inline, so it means you come out one side. All your pins come out one side, if I get back up there. And they're they're in line. These are called dips. What does that mean? Dual inline pack. So notice it's got two pins down each side, and they're in line. So these are called dips. These are called SIP. These are actually what's generating the frequencies and everything. Of course, y'all know what that is. This device right here, I'm not going to turn it. That's the potentiometer. I wish I could pass this around. Yeah, you can actually see where we could turn it right here. So this is, and we have potentiometers smaller than that guy. And so these are the integrated circuits that actually have the function generators and that kind of stuff. So on this thing, if it works after I dropped it, but I believe it will. Here's where the neon light's at. This is the neon light. It's actually inside the power switch. You got it turned off. And these are just inputs that you can use. But this is the output for a clock. So this is a digital clock. This is a function generator. Or this is a sine wave generator. And that's inside there. So we can get a sine wave out of here, function out of here. These are just switches that you can turn on or off. And you'll use this for, if you take digital, you'll use these up here for digital. And of course you'll output up here with your digital devices so you can see how they work. So, and this is what I need to show my other class. I'm going to have to do that. And you can see this if I put this on the oscilloscope. When I fire it up, I'm going to show you what actually happens with the oscilloscope. But you'll see what actually goes on when I come over and flip that switch down. We can't see it with a meter, but we can see it with a oscilloscope. So guys, what do we get for, are we ready? So what wattage is our zener going to have to dissipate? So what happens with the zener? So if my input voltage goes up and my load voltage stays the same, and if my input voltage goes up and my load current stays the same, what happens to zener current? Yeah, but something's going on with the zener. So if this guy, let's say this guy right here is conducting 10 milliamps, and this guy right here is conducting 10 milliamps. That means my total current over here would be 20 milliamps. Okay. But if this voltage goes up, and this is if this voltage right here goes up, that means this guy here is going to have to drop more voltage. This guy over here is still pulling 10 milliamps. That means the zener current's got to automatically do what? Yeah, it's got to go up. So zener current varies in the same direction as input voltage. If the load current doesn't change. So if input voltage goes up, zener current goes up. If input voltage goes down, zener current goes down. It varies in the same direction. So we have a device that dynamically changes its opposition to try to maintain a constant output. What happens if load current goes up? And the input voltage stays the same. So if input stays the same, this guy might be dropping 3 volts, which means the current flow through it's going to be the same. But if load current goes up, this guy's conducting the same current, it means zener current has to be going down. So zener current varies with the opposite direction of load current. It varies in the same direction as input voltage. And it's constantly changing its opposition. So this, like I said, this is the first device that we had that's dynamic. It is not a resistor. It is a solid state device. Resistors cannot change their resistors. If you got a 100 ohm resistor, by George, it's going to be a what? A 100 ohm resistor. But a zener is dynamically changing what they call its impedance because it's changing. But it's changing its opposition to try to maintain a constant output. That will be on the test. Okay, guys, let's see. About time to go. Got the circuit hooked up. We'll fire this puppy up next class. Take it through its design parameters and see if we got a good design. So right now we're using 100 ohm for RS. We're not gonna measure current. We're gonna come over here. We're gonna calculate what this 100 ohm resistor is supposed to drop for the current. Then we will adjust our pot wire to the rheostat to make that resistor drop that much voltage, and then we'll know, and then we'll measure our zener voltage. We'll measure our voltage across our load and see what it does.